では続きまして、第2位エクストリームエッジ賞を受賞しました TeamIRAFM さんです。では、プレゼンテーションの方を始めていただければと思います。
Okay.
Perfect.
Okay. Good afternoon for you from here, from the Czech Republic. It's very nice to be here and to join this event about this contest. So my name is Marek Weigl. I'm here with my colleague Petr Hurtík, and we are from the University of Ostrava, from the institute with short abbreviation but very long name. And this institute primarily aims at the development of novel methods, not only in image processing, but also in different fields like time series and so on. But me and my colleague and another colleagues in our team, we mainly focused on image processing, and now we have transferred to the domain of neural networks. We both made the PhD on the University of Ostrava. Petr is aimed slightly more on applied mathematics, and I'm aimed slightly more in the field of informatics and programming. And I'd like to know that we have already been in Japan and have been to Tokyo about 2 or 3 times, and we do enjoy or we are enjoying our presence in Japan. So we very looked forward to join this competition, and unfortunately, due to COVID situation, we are not to participate directly there. So we need to do this online. Okay. So, sorry. About our motivation, as I said before, we are developing a special approach together with some industry company aimed to very similar task to detect objects in the traffic scenes like pedestrians, cars, animals, and so on. And we have developed some new improvements in this field and try to compare this approach in the worldwide competition. And also, the second point, we want to establish a cooperation with some Japanese researchers. As I said before, we have made some visits to Japan on the conferences and have shared some knowledge. And we are looking for the further improvements and further cooperation. Firstly, let's talk now about our solution. Firstly, we have or had a quite limitation in our available hardware. Our solution was built on 2, let's say, standard gaming computers with price about $2,000. One was equipped with RTX 2080 card with 1 GB. The second one was on the lower level RTX 2060 with 8 GB. And we are trying to keep the idea that the good idea is better than strong hardware. So we try to improve ideas which fits our hardware and also moves us forward in the quality of the solution. Okay, here I'll present the basic scheme of our solution. At the beginning, as we obtain the image, we do some image augmentation, of course. And then the second part is the basic bounding box detection. As I mentioned before, our solution is based on YOLO, a neural network, which we have extended in some way called PolyYOLO. We have trained 5 different models and aggregated their results together. The second part is based using something what we call refining the bounding boxes, the rectangular areas. And this part improves the precision of the bounding boxes. Then, as YOLO does not contain the classification, or as we did not use the classification, we used the separate classifier, And then we need to use some tracking of the objects using our custom solution called Matcher. And as mentioned in the previous presentations, we have some well done post-processing aimed at the filtering and improving the quality of the final result.
Okay, konnichiwa. My name is Peter, and I'm going to describe the solution. So firstly, we augment the input data. We use standard augmentation known from OpenCV, such as Flips and so on. And then we have two custom augmentations. The first one takes half from one image, half from the other image, and combine it together. And the second augmentation is when we in-paint objects. So we take boxes from different images and put them or in-paint them into a new image, where we also need to check that there is no other object. So put them into a free place. And I think that this augmentation helps us to train the neural networks much better and to postpone overfit. And that is also probably the main reason why we jumped from the sixth position into the second position, final position. Okay, for the box detection, we used PolyYOLO. As Marek said, it is our own development. Here you can see a link to the paper where we describe it. And because of the original YOLO of the third version is not so precise, we improved it. So instead of 3 output scales, we have only single output scales because there is a problem with rewriting of labels in original YOLO. It's written in the paper. And also we have some new upscaling, which is called stair-step upscaling, which helps to propagate the feature maps in a better way. Also, we changed slightly the original backbone and we improved it by squeeze excitation blocks. Finally, this new proposal is faster than original YOLO, and it is about 20% more precise on COCO benchmark dataset. So this is our main tool for detecting the boxes. As Marek told you, we have 5 models. They are trained with warehouse resolution. So we downscale the input images into the resolution, as you can see here, and with different batch size, because it is also depending on our graphic cards. So therefore the batch size for the last 2 models are quite slow, only batch size equal to 1, which we know it's not so ideal, but we have limited sources for that. So we realize 5 application of these PolyYOLOs to the input image, detect boxes, and then we combine them together by weighted box fusion into the final prediction. And then, because the boxes still, or some of the boxes are not so precise, so it means that we are under the IOU 0.5 threshold, we implemented a new way how the boxes can be refined. And with this we can create a better or more precise boxes, which also improve the scores. So for that, we wrote an easy network where we use efficient net of the third version or third type as a backbone, and we predict a new coordinates for cropped image. And currently we wrote a paper about it and we sent it to the ICLR conference and we are waiting for the review process. So in final, we will publish it again publicly. Okay, and because sometimes we also detect some false positives, we implemented a classifier where we trained it on the crops from the images. So we take some crop, create from it a letterbox image, and train over it a classifier. And with that, we are able to distinguish what is a false positive, and we remove such false positives. That is sometimes useful for vans because Here, the aim is to detect only standard cars, but the Japanese cars, at least for us as we are European, are similar to ones. And also it seems that it's similar for neural network for the YOLO. So it is better to realize here also the classification. And for that we have also, we also have EfficientNet as a backbone, and it's standard network, and there is nothing new. Okay, then we realize tracking via matching. So we wrote our network. It is Siamese network, where we use the standard contrastive loss, and we use the network to track the objects. So we take objects from one frame and match with objects in another frame. And yes, I have to say that it is not so easy, and we wrote there a lot of rules to realize precise tracking, even if some object is missing. But as we saw in the comparison presented by the organizer, our tracking is not so great. We are the worst from the top 3 solutions. We are probably better in the detection, and here there is still some space for improvement. So I think that it was not so good to develop our tracker. It would be better to use some state-of-the-art tracker, but our motivation was to realize our development in all the parts. So that is the motivation.
Okay, and at the end, we are returning to the final processing to post-processing. I think that we are making some things very similar there with the other teams. The first post-processing part was the deletion of the small boxes. There was some threshold defining the minimal size of the box. We lowered this threshold a bit, and we are deleting the boxes below this threshold size. The second part was the deletion of the boxes with a low occurrence. There's a rule that the box must appear in at least 3 frames in a row. So we omit the boxes which does not fulfill this condition. And finally, as also mentioned in the previous presentation, filling the gaps of missing objects which are hidden behind some obstacle. So we are trying to detect the objects which are missing in the frames, and we added them into the missing frames. So as the conclusion, we of course do congratulate to all the participants and the top positions. I'd like again to thank also the participants, but also to the moderators or everybody who prepared this competition, as it was a very nice experience. Also to the sponsors, which allowed this participation be processed. And we hope that we will see with some of you in Japan after the COVID situation will disappear and the world will change. So thank you for your time and for your attention. And at the end, before the questions, we are ready to show you our video from the, I think this is from the free data set from the Tokyo streets. So you can see how it works in the real life. Thank you.
Yes, here is the movie which we downloaded from YouTube. It's under free license, and we applied on it our solution. The distribution of this data is a little bit different, as there is different resolution and different camera and so on. So the performance is slightly lower than on the test data, and we didn't realize some fine tuning here, just put the model and realize the precision. So we can conclude it that our solution is even somehow applicable to real life, and it is working also in some generalized data, as you can see here. I also do want to say thank you for the organizer and sponsors. We really enjoyed the competition. It was fun for us, and I also enjoyed the discussion in the forum, and I'm happy that I met some new people, and I hope that we will be in touch also in the future. So, arigato gozaimasu. We have some troubles with sound, so yeah, I see now the questions in the chat. So the first one is, if we fine-tuned on pre-trained something. We tried to pre-train our models on open data. I think it was Waymo dataset because it was allowed, but it didn't help us. So we forbid it, and the final resolution is not pre-trained. The second one, what loss and optimization did you use? Yeah, for the YOLO, it is custom loss where we have mean square error for X and Y coordinates and categorical loss for width and height, if I remember it correctly. Also, our solution is available on GitHub, so you can see all how it is working. For the optimization, we use ADA Delta because I like it much more than Adam because it converges faster, in my opinion. And what is most important, residual block type or layer? Okay, if we made some analysis, so there is no sum layer, which is really important, at least in the YOLO, where we have only one output scale. So it is really important, and the layers are cooperating here together, so there is not some major layer. So I hope that I answer it, and if there is some other question.
Thank you. Other question or comment on this? If you have comment, question. So thanks for your presentation, Dr. Kane, and I will move to the next presentation. Thank you very much.
ありがとうございます。
ありがとうございます。